In this lecture, we shall study viscosity, drag force, and terminal speed of a body moving through a fluid. Okay, first we discuss viscosity. We know that both liquid and gas are known as fluid. When the molecules of a fluid flow parallel to the direction of motion of the fluid, then this motion is called streamline motion. If the molecules do not advance parallel to the direction of motion of the fluid, then the motion is called turbulent motion. How much resistive a fluid is while flowing is measured by its viscosity. In the case of flow, honey is more resistive than water. Hence, honey is more viscous than water. The viscosity of a fluid is similar to the friction of two solid bodies. Fluid does not have any definite shape because their intermolecular forces are negligible. A fluid which flows above a horizontal surface may be imagined as divided into many layers. The layer attached to the lower surface is stationary and other layers are moving. The relative velocity varies with the distance from the lower surface. The greater the distance, the greater is the relative velocity. At time of flow, a layer in the fluid makes a friction with the adjacent layer and it opposes the relative motion of the layer. As a result, different layers move with different velocities. The friction between different layers of a fluid is known as viscosity. It may be defined as follows. The property of fluid liquid or gas by virtue of which it opposes the relative motion between its different layers is called viscosity. As friction opposes the relative motion of two solid bodies, viscosity opposes the relative motion of two layers of a fluid and tries to retard its motion. Hence, viscosity is also called internal friction. Viscous force does not act in case of static fluid, but acts only when the fluid is in motion. The difference between the frictional force and the viscous force is that while the magnitude of the frictional force does not depend on the area of the contact surface, the magnitude of the viscous force depends on the area of the layers of the fluid. Further, the viscous force depends on the velocities of the layers of the fluid and the distance from the static layer. Now, what is coefficient of viscosity? Let us first discuss the Newton's law of viscosity. If there is a relative velocity between two layers of a fluid, then the tangential viscous force, which acts opposite to the flow, is directly proportional to the surface area A and the velocity gradient dV by dy of the layers at constant temperature. if there is a relative velocity between two layers of a fluid, then the tangential viscous force call it say F, which acts opposite to the flow is directly proportional to the surface area let us call it capital A, and the velocity gradient called dv by dy, where y is the perpendicular distance from the surface of the fluid and perpendicular to the surface of the layer at constant temperature. Okay, mathematically, so the force is proportional to this area when dv by dy is constant and f is proportional to dv by dy when a is constant. If we combine these two, we get f is proportional to a into dv by dy when both a and dv by dy change. If we put equal sign, then we'll have to put a constant. Let us say this constant is eta. Okay, here eta, this proportionality constant, is known as the coefficient of viscosity. This is the Newton's law of viscosity. Now, what is the coefficient of viscosity? The tangential force required maintaining unit velocity gradient between two layers of a fluid of unit area at constant temperature is called the coefficient of viscosity of the fluid. The unit of the coefficient of viscosity eta is Newton second per meter square. So is Newton second meter to the power minus 2. Now, if we say the coefficient of viscosity of water is 10 to the power minus 3 Newton second per meter square, what is the meaning of this? The meaning of this is that if two layers of water of 1 meter square area are at a distance 1 meter from each other, then 10 to the power minus 3 Newton force is necessary to maintain a relative velocity 1 meter per second between them. Okay, now effect of temperature and pressure on viscosity. There are effects of temperature and pressure on the viscosity of fluids. The effects of temperature on viscosity. The effect of temperature on the viscosity of liquids is found from many experiments. It is found that the magnitude of the coefficient of viscosity of water at 80 degrees centigrade is 1/3 of that of at 10 degrees centigrade. But a definite relation between the temperature and the coefficient of viscosity of liquid is not found. Different scientists have given different formulas. One such formula is this: logarithm of the viscosity is equal to a constant A plus B by T, where A and B are constants and T is the temperature in Kelvin. A and B are constants. So you see, if you increase the temperature, then the viscosity decreases. Okay, this is viscosity of liquids. For gases, effect of temperature is the viscosity of gases increase with the increase of temperature. This is completely opposite to the previous case of liquids. The coefficient of viscosity of a gas is directly proportional to the square root of its Kelvin temperature. So is eta is directly proportional to square root of temperature. Now, effects of pressure on viscosity. For liquid, viscosity of liquids increases with the increase of pressure. The effect of pressure on mineral oil is very much noticeable. And gases. On the basis of kinetic theory of gas, Maxwell states that there is no effect of pressure on the viscosity of gas, and it is applicable for a large range of pressure. But in case of low pressure, exception is also seen. Okay, next we shall consider drag force and Stokes law. Stokes law. Here we discuss the viscous friction force that opposes the motion of an object relative to a fluid. Examples include the resistive force of water on a swimmer and the resistive force of air on a car and a bicycle. These viscous friction forces are often called drag force. Okay, viscous friction forces are called drag force. When a ping pong ball dropped from a building, if the ball falls slowly, laminar flow occurs. Streamlines of air pass the ball as it falls. As the ball's speed increases, the flow of air past the ball becomes turbulent. The onset of turbulence is predicted by a different form of the Reynolds number. So the onset of turbulence is predicted by a quantity known as Reynolds number. And this Reynolds number is defined by this V L rho divided by eta, where V is the object's speed which is moving through the fluid. L is the object's length. Rho is the density of the fluid. And eta is the viscosity of the fluid. Okay, if this Reynolds number is smaller than 1, then the flow of the fluid is usually laminar flow. smooth flow. But if the Reynolds number is greater than 1, then the flow of the fluid is turbulent. Flow will be turbulent. Now, if the flow is laminar, smooth flow, if the flow is laminar, the drag force increases approximately in proportion to the object's speed. Relative to the fluid. That means if Fd is the drag force, then this can be written as capital D into V, where Fd is the drag force on the object moving through the fluid, and V is the object's speed, and D is a constant. Now, for this situation where a circular object is circular with radius r, small r, if the object is circular with radius small r, falls at speed v through a fluid with viscosity eta, then the drag force for the laminar flow is this. The drag force then is equal to 6 pi eta rv. This is the expression of the drag force on an object in the form of a circular object of radius small r, and this equation is called Stokes law. On the other hand, if the fluid flow past the object, moving object, is turbulent, then the drag force increases approximately in proportion to the square of the object's speed relative to the fluid. Past the moving object. Is turbulent, then the drag force increases as v square, where v is the relative speed of the object with respect to the fluid. So we can write down the drag force in this case is k into v square, where k is a constant. It can be shown that this k, if the fluid is an air, then k is equal to half CD rho into A, where rho is the density of the air and CD is a unitless number called the drag coefficient. Unitless number. CD is a unitless number. CD is known as drag coefficient. And rho is the density of air, and capital A is the cross-sectional area of the object as seen along its line of motion. Okay, now we prove the Stokes law. Stokes' law was this: 6 pi eta RV. Okay. It can be reasonably assumed that the opposing force, the drag force, is depends on eta. If you consider a spherical, body, then its radius, and on the velocity, relative velocity of the object with respect to the fluid. So let the drag force is equal to some constant k and r to the power x, eta to the power y, and v to the power z. We apply the dimensional analysis. Okay, dimensional analysis. Now our target is to find x, y, and z. The dimensional analysis, so we write down the dimension of FD is equal to dimension of R position, dimension of eta to the power y, and dimension of v to the power z, where k is a constant here. Now we know that the dimension of force is ml t to the power minus 2, where m is the mass, l is the length, and t is time, and this r is l to the power x, and we know the unit of eta is m l to the power minus 1 and t to the power minus 1. So power y, and velocity is l t to the power minus 1. This. So this is equal to m to the power y, l to the power x minus y plus z, and t to the power minus y minus z. So we have, this is m l t to the power minus 2, equating the powers. We get 1 equal to y, 1 equal to x minus y plus z, and minus 2 equal to minus y minus z. Okay, solving this, we get x equal to y equal to z equal to 1. Therefore, the drag force is k into eta into r into v. Now, from advanced mathematical analysis, we can show, we are not doing here, but can be shown that k is equal to 6 pi. Therefore, the drag force is equal to 6 pi eta RV, which is the Stokes equation, Stokes law. Okay, our final topic is what is terminal speed and the expression for terminal speed. An object falling through a fluid eventually reaches a speed where the force pulling it in one direction is balanced by the opposing drag force. The net force on the object is zero. It no longer accelerates and continues to move at a constant speed called its terminal speed. Okay, so the terminal speed of a skydiver is approximately 54 meters per second, whereas that of a falling raindrop is about 12 meters per second. A red blood cell falls in a beaker of water with a terminal speed of about 10 to the power minus 7 meters per second. Okay, now when an object moves through a fluid, and as I mentioned, that if the force because of friction, the retarding force is equal to the force uh, force for which the body is moving, they are equal, then there will be no net force. And with a uniform velocity, the object will move. This uniform velocity is called terminal velocity. The magnitude of it is known as terminal speed. Now, expression for terminal speed. Okay. Let us consider a sphere. We consider a sphere with radius small r and falling through a viscous liquid. Okay, this is weight of the spherical object, and there will be a buoyancy force, and also there will be a drag force. Now this weight of the object must be equal to the drag force plus the buoyancy force. Okay. Now the buoyancy force is, which is equal to the weight of the displaced fluid by the spherical object, which is volume is 4 by 3 pi r cube, which is the displaced fluid, and rho f is the fluid density, and g is the acceleration due to gravity. So this is the force. Volume into density is mass and multiplied by g. So this is the weight of the fluid displaced by the spherical object, and the weight of the object, which is the mass, which is volume into density, so 4 by 3 pi r cube, and rho, this is the body object, and g, and the buoyancy force, that is, this is the actually, this is the drag force, d, this is the buoyancy force, and this is the weight of the object, and this is the drag force, and we know this is from Stokes law, 6 pi eta rv. Now if we apply this to this equation, then we'll have 4 by 3 pi r cube rho object and g is equal to 6 pi eta r v plus 4 by 3 pi r cube rho fluid and g. The equation can be written as 6 pi eta r v equal to 4 by 3 pi r cube rho b g minus 4 by 3 pi r cube rho fluid g. And if we take common 4 by 3 pi r cube, and we'll have here rho b minus rho f and g. Okay, from this equation we can find out the terminal velocity vt, which is equal to twice r square rho b minus rho f and g divided by 9 eta. Okay, so this is the expression for the terminal speed of a body or object which is moving through a fluid. And this is the last topic of this chapter 3. In the next chapter, we shall consider heat and thermodynamics.